temperate regions will become more warmer. The tropical and subtropical regions will come under more stress. There will be more need of water. There will be more diseases. The wheat flora is likely to change. And generally, particularly in these cold living plants, there is a possibility of yield reduction, particularly in wheat. So, how to address the climatic changes? How to reduce the impact of climate? How to prepare ourselves to adaptation and mitigation strategies to keep up with the climate change? Yeah, one of the strategies is to reduce the greenhouse gas emissions. For example, we use a lot of fuel in industries. We can shift, say, to solar energy, isn't it? Or hydroelectricity. There are possibilities. Similarly, we can reduce the greenhouse gas emissions, and the other strategy is to sequester carbon. If we apply more and more organic manures to the soil, this way we can, soil is a very big sink of carbon. We can use it as a sink, and we can, meanwhile, side by side, we can increase the soil health by adding more organic matter and organic carbon to the soil. Then, 20 or 30 years before, scientists visited some of the parts of Brazil, where they found that terra preta soils are very, very productive for hundreds of years. Then they further investigated that region, and they saw that it was black in color and very rich in aromatic carbon. Aromatic carbon is actually the buried material. When we heat up this organic carbon at a temperature of around 450 to 500 degrees Celsius for a sufficient amount of time, say 2 to 3 hours, and in relatively very small concentration or no oxygen. If we burn it in oxygen, it will oxidize, it will produce a lot of carbon dioxide and other sulfur gases, and then it will reduce to ash. The entire carbon, say 90% of the carbon, will go into the atmosphere as a greenhouse gas, and the rest mineral components, say potassium, calcium, some phosphorus, and other minerals we will receive as ash, say 1%. So that is open burning in presence of oxygen. But now, when we put this organic material, say a wood material or any biomass from our crop plants, in relatively anoxic conditions, then we heat it up at 450 to 500 degrees Celsius, then we expect this organic carbon to convert into aromatic carbon. Now, what is the property of that aromatic carbon? Say this material, this is from walnut shell. Walnut shell, when we remove the kernel from walnut, then the shell remains, and it's a very rich source of carbon, like our coconut shell. And this material has higher percentage of carbon. The more the dense wood is, the more will be the retention of the carbon when we pyrolyze it at 450 or 500 degrees Celsius. So this is one of the raw material. Now what is happening in this case? This aromatic carbon is actually benzene ring. Aromatic carbon is recalcitrant to decomposition by the microorganisms. Whenever we add normal, say cellulose or lignin or hemicellulose materials to the soil, the microbes act upon it, they convert it into carbon dioxide and use the energy for their growth and some nitrogen as protein, and they build their bodies, and this way in 2 to 3 years entire organic carbon that we add to the soil is converted into carbon dioxide and released into the atmosphere. But this kind of carbon, heated at a particular temperature for a sufficient amount of time and at a certain concentration of a very low concentration of oxygen at a certain pressure, there are certain conditions under which typical or characteristic biochar is produced, that lasts in the soil from 1000 to 45,000 years. It doesn't degrade in the soil, it doesn't decompose in the soil. Now what has happened actually? We have converted atmospheric carbon dioxide through the process of photosynthesis into biomass. Then that biomass we have converted into biochar by pyrolyzing it, by heating it at 450 to 500 degrees Celsius for a sufficient amount of time. And then that aromatic carbon actually is the atmospheric carbon that has become recalcitrant to decomposition. And then we have added it after certain processing, we have added it to the soil. And then soil has acted as a store of carbon that is recalcitrant, that is very, very hard to decompose. This way, this effect is called a drawdown effect. We are drying down atmospheric carbon dioxide in the shape of aromatic carbon, and then we are adding it to the soil. So this is the fundamental principle of biochar production and biochar application. Now, how to produce it? We get biomass from wood. say forests, or we get biomass in Kashmir from our apple orchard. We get from these saw industries. There are 400 registered sawmills in Kashmir, and we get thousands of tons of wood shade. जिनको पसेल हम बोलते हैं, ठीक है? उसका it has a price tag. It is 300 rupees per quintal. Say this walnut shell is 400 rupees per quintal. But there is rice chaff. So any इस तरह का conversion, इतने sample थे. We in our own campus we produce 25 to 30 quintals. That means 3 tons of rice chaff, and that rice chaff is entirely wasted. It rots there where it is stored and then it vanishes. So if that 30 quintal of rice chaff is converted into at least we get 35% recovery, it will be 1 ton of biochar. And this kind of material we heat up in this pyrolyzer, and then that is converted into this kind of biochar. The last one is rice chaff. Simple material. In Punjab or in certain other countries where rice husk means when we mill rice, we get that उसको कम बोलते हैं, हम यहाँ कम बोलते हैं, उधर से में कूम बोलते हैं. That is fed to cattle here. But in certain states of India, say Punjab or Haryana, it is again a waste. That is rice husk. Rice husk can also be converted into biochar like this rice chaff. So the other material I told you, walnut. Walnut we remove the kernel and we can use it for biochar. And this is high quality biochar because it has high carbon content. And then we have this is wheat straw. From this wheat plot we get wheat straw that can be also converted. And then we have apple prunings. In Kashmir we have more than 1,64,000 area hectares under apple orchards, and every year we prune the apple trees, and then that pruning is actually generally burned and converted into charcoal. Now charcoal and biochar is different. Charcoal is produced in open air, but in this biochar is produced in closed containers, as I told you earlier. Then we have rice straw also. Sometimes it is wasted, and then we have this rice chaff. At least 4 or 5 materials we have produced so far here. Now, what is this kiln? This kiln is actually a drum inside it. Then drum we have closed it with a lid. Then there is a central pipe. Oh, choti wali bukhari now is it holds I should show this one. This is smaller version. This is smaller version of biochar stove, right? This is the outer chamber here. Here you can see this is the outer chamber where fuel is placed, fuel is fed, and then this is the inner chamber here where the feedstock, whatever we convert into biomass, that's called as feedstock. So this feedstock is placed here. Then we close the lid. Here, this is the lid, and then what we do, we start heating it up from the below. Then we attach another pipe here. Then what is the role of that pipe? Can anybody tell?
Yes.
Can anybody tell?
Yes, sir.
No, what happens when it is heated up, and then we place it when it is heated up, then it is called as thermal siphoning. It's called as thermal. A lot of hot air moves very fast inside it. When air moves fast from this point, then it sucks more air from the bottom, and that more diffusion of oxygen will result in fast burning, and it will produce more heat. So that's this is समावार में पुराने ज़माने में हम चाय बनाते थे, तो उसको ये लोअर पाइप रखते थे ऊपर. This is called thermal siphoning. This is because of this thermal siphoning we place this pipe above the kiln, right? And then we thought that why to waste this energy? We can also modify it by using this structure here. We can place a pot here to cook. At the same time we will produce heat, and at the same time we will produce 1 or 2 kg of biochar also, depending on the recovery percentage, other conditions. But it should be used outside the kitchen, because it may produce some carbon monoxide and other poisonous gases. So inside just like this we have placed it outside in the open. So that is very important precaution that has to be followed. Now regarding this one, this one has a drum inside. There is one central pipe here, and below that drum we are burning this fuel, and inside the drum we are placing the feedstock. Then from the central pipe the exhaust goes out, And we also place in the space between the drum and the brick wall, we place some fuel in the bottom and as well as the sides, then a little bit at the top also. Then it starts burning. After 1 or 1.5 hours, we attain the characteristic temperature of 450 to 500 degrees Celsius. Now you will think that how we know that what temperature we have achieved. We have achieved. Now you can come here. You can see 210 degrees Celsius we have achieved. In next half an hour we will achieve around more than 400 degrees Celsius. Sometimes in the literature you will find only 300 degrees Celsius. But in most of the literature we have seen that it is the temperature we should achieve for 2 to 3 hours is 450 to 500 degrees Celsius. If the material is like walnut shell, it may cross 300, 600. Because it produces a lot of heat, more carbon and more heat. So this is a thermocouple. Thermocouple, when we join two metals of different nature, and then when we heat one of the points, that's called thermocouple, then it will produce voltage, it will produce electric current. And that electric current is measured by this meter, and that electric current meter has been calibrated to temperature. At a certain voltage, at a certain current, this much temperature has been achieved. So that has been calibrated, and this thermocouple we have placed it inside the feedstock. So when that feedstock reaches that temperature, we record here. Then we plotted the time. For example, we start the kiln at 11. Then we, after 5 minutes, we record the readings, and then we see in the graph, yes, for 2 to 3 hours we have maintained a temperature of more than 40 degrees Celsius. So that is the role of this thermocouple. This is very, very important to record the temperature. Otherwise, if it is below, for example, for 200 degrees Celsius, or if it goes above 600 degrees Celsius, then we may not call it as standard biochar. When we heat it up, you can go there now. Then we will close it from the bottom to cut off the oxygen supply. Then if some of the material is not is still unburned, it will slowly burn it, and then finally next morning it will cool down. Still sometimes we feel some heat inside it because it is completely covered by the jacket to reduce the loss of heat and build the heat. Otherwise, in the open, if we heat it up, it will require more energy. So loss of heat will be there. So that's why we have the insulator around it. So that is the point. Another on a more finer level, we also use perlite as the insulator. Between two brick walls, we can place perlite to further reduce the loss of heat. Otherwise, this is covered by clay, cob, mud, and there is a brick inside it. It's a good insulator and very, very low cost, right? So that was all about the production of biochar. One of your students has also he has on a copper vessel. But one thing we should keep in mind that can be used for a laboratory scale. If we want to produce, for example, for an experiment for a 1 canal area, we require 2 to 3 quintals. So it will take a lot of time to produce 2 to 3 quintals of biochar for that purpose. But if we regularly in a household we use this type of biochar, then every day we can produce 1.5 kg or 2 kg every day. Then it will go on adding, and for household use by the communities, we can definitely use this because it is a year-long practice that can be adopted by the farmers. And number of stores are available for the production of the biochar, and for a larger scale, this kind of kiln is needed, why we use a 250 liter drum, right? So that was all about the production part of biochar. Now, how to use it? We cannot use it such a big size. We have to micronize it. If we want to add it to the soil or want to use it as a carrier, it has to be micronized. It has to be broken by a grinder, right? By I think 1 micrometer to 5 micrometer is the right size for the use of this biochar as a carrier for the different types of microbes. So one possibility is the use of this biochar as a carrier. The other more important use of the biochar is for the agricultural purpose. This biochar is a rich source of carbon not only, but it is also has very high cation exchange capacity, CEC. It will absorb many types of anions and cations, more cations. Then what it will, for example, if we add phosphorus to the soil, or if we add nitrogen, if we add potassium, if we add many other micronutrients to the soil, it will absorb them. then it will absorb them. Once we grow crop plants on the soil, it will slowly release those nutrient ions, and the plant will be able to take it up. Now, how it will help now? It will help, for example, we add phosphorus to the soil. If it is absorbed by the biochar, it will be released slowly, otherwise it will be fixed in the soil. In acidic soils as aluminum and iron phosphates, and in alkaline soils as a calcium phosphate. So it will be no longer available. But if we use this one, it will increase the phosphorus use efficiency. Similarly, it has the capacity to absorb N ions, for example, nitrate ions. Then it increases the nitrogen use efficiency also. So that's very, very important. Number 3, it is a very rich source of potassium. While we add biochar in a sufficient quantity to the soil, we need not to we can reduce the dose of potassium. So particularly, you should keep in mind that if we produce biochar from wood source, say pear wood or apple wood or silex or poplar or whatever, it is high carbon but low nutrient. When we produce biochar from crop residue, it is low carbon but high nutrient. So that way, if we produce biochar from crop residues, it is a source of nutrient also, particularly phosphorus, potassium, calcium, and many other minerals. But some of the nitrogen is lost, because whenever we heat any biomass at a high temperature, the nitrogen will be converted to nitrous oxides, and nitrous oxide is a gas, and it will go up. So it is a very poor source of nitrogen. Number 1. Number 2, you cannot use biochar exclusively. Exclusively means only biochar is not sufficient. It will absorb nutrients and it will create stress. Because it is just a carrier, it's just a medium. It is not the principal source of nutrients. It is a soil amendment that modifies the properties of the soil, because it absorbs. Then how to address that problem? We can blend it with many materials. You have FIM, well decomposed, you have vermicompost, you have compost, you have any plant material that is well decomposed can be mixed with it to enrich it and to enhance its value as a source of, not only as a source of carbon, but as a source of plant nutrients also. So those blends have to be, for example, if we micronize it and that add 1:1, or we add 1 part of biochar and 2 parts of any this decomposed material, say vermicompost, then that can be used as a organic manure, as a fertilizer for our soil, and it can be used in organic farming as far as told, because it is a natural material, it is organic in nature, and it is allowed in organic farming. But if you want to add fertilizer, you can do that one also. 2% nitrogen, 2% N, and 1% phosphorus can be added to it. No need to add potassium, because I told you that is a rich source of potassium. We can enrich it in conventional farming. We can enrich it with 2% nitrogen and 1% phosphorus to make more phosphorus and nitrogen available, and that too in a very efficient way. So that's how it increases the nitrogen use. Number 2, it also reduces the emission of greenhouse gases. Because when it absorbs nitrogen, for example, then naturally the emission of nitrogen gases will be reducing, and it also reduces the carbon dioxide emission from the soil. Overall, it reduces the greenhouse gas emission. That way, it is also helpful for mitigating the climate change. Number 1. Number 2, it has twofold higher water holding capacity. Whenever you make a material, we have already prepared some blends and we have put on the stall on that day. You see, it's a very fluffy material, it's a very loose and low bulk density material. When we add it to the soil, it absorbs more water, and then what it does, it releases the water very, very slowly for the use by the plants. In rural areas, if some of you may be from rural community, when we make charcoal in our houses, then we sprinkle water on it to extinguish the fire. Then we notice that it takes a long time for the charcoal to dry. This is because it has very small micropores inside it. It holds water strongly in those microcapillaries, and then it takes more time to dry. So what does that mean? If we add the same material to the soil and then we irrigate the soil, it will evaporate, it will lose the water very, very slowly and hold more amount of water because of its porous structure. And that way, it also increases the water holding, water use efficiency. Whenever you add some water and then you produce from water some biomass, you will be able to produce more amount of biomass from less amount of water. That is called water use sufficiency. So that is the other benefit of this adding biochar to the soil, either exclusive or blending with soil. If the soil is fertile, maybe we can also add small quantities exclusively. Otherwise, normally we have to blend it with some nutrient-rich material, as I told you, the vermicompost, or a, FIM, or whatever is available in the house. Then to enrich it, we can add the dose to enhance its nutrient supply. So I think that was all about. If you have some